Hi, welcome to Knowledge Quest 10 on threaded fasteners. I think you'll find this Knowledge Quest pretty interesting. It'll be different than the other ones we've done because it'll be more conceptual and just some new material. So mechanical fasteners at first glance might seem to be one of the least interesting aspects of a design, something we often overlook, but in reality, they can be one of the most fascinating aspects of a design. And you could presumably spend your entire career specializing in fastening methods. The success of a design often hinges on the proper selection and use of fasteners, and we'll talk a lot about that in this video. And the design and manufacture of fasteners is a huge part of our economy. So a Boeing 747 has about 6 million parts, half of which are fasteners, if you can believe it. So that's 3 million different types of nuts and bolts, rivets, and screws. And each fastener in a Boeing 747 costs several dollars. So a good design is going to minimize fasteners. Also, a good design will minimize fasteners for the fact that components or systems are most often susceptible to failure at interfaces or connection points. So a broad definition of mechanical fasteners, it is a device that is used to mechanically join or fasten two or more objects together. And there are so many different types. In general, they can be divided into non-permanent and permanent fasteners. So permanent fastening types would be things like welding, gluing, or riveting. And in this class, we're going to focus more on non-permanent fasteners. So a wheelchair is a really good example of a device that has both permanent and non-permanent fasteners. So the permanent fasteners might be the weld lines in the frame, and then the non-permanent fasteners might be the things like the bolts or the screws that hold other components to the frame. Non-permanent fasteners enable parts to be assembled and disassembled repeatedly. Two groups, general fasteners include keys, pins, retaining rings, etc. So these are things that are often used with shafts, and we've studied them previously. And then threaded fasteners, bolts, screws, studs, set screws, etc. And threaded fasteners are the most widely used type of non-permanent fasteners since they can be easily removed, then reused. Not all parts of a threaded fastener can be reused though, and we'll talk about that later. So some top-level information about threaded fasteners. Broadly speaking, there are 3 different types. A bolt has a head on one end and threads on the other end paired with a nut. A screw is similar to bolts with a head on one end and threads on the other end, usually has longer threads than bolts. So if you see here, there's a large part of the bolt that's not threaded, and then there's a small portion that's threaded. And we'll actually talk about why this is. And then with the screw, you have a longer part of the entire length that is threaded. And then a stud is a rod that is threaded on both ends, and a nut may be used on one end. I've posted a document on Canvas that is similar to what you see here, different types of fasteners and their characteristics, and you'll be referencing this document for a couple of questions on your quiz. So bolt versus screw, what's the difference? You may have noticed that these terms are sometimes used interchangeably. In practice, however, the basic difference between a bolt and a screw is that a bolt is usually intended to be used in conjunction with a nut, where it will be tightened or loosened using the nut. A screw, on the other hand, is intended to be mated with an internally threaded hole, and the screw head itself is used for tightening and loosening. Okay, this is probably my favorite video of 329. It's called Screw It, Intro to Fasteners and Bolted Connections. And FYI, a lot of questions on your quiz come from this awesome video. It's about 12 minutes long, and again, I suggest some popcorn.
Fasteners are some of the most important components in any machine, but they're often taken for granted. It's vital to correctly choose and use them, or else the mechanical integrity of a product is at risk, and there can be devastating consequences. Thread type, preload, material choice, coating spec, drive selection, and more all need to be understood and applied properly. In this video, we're going to go over all these fastener topics and many more, so that you know the nuts and bolts of nuts and bolts.
Fasteners come in a wide range of shapes and sizes, from the tiny microscrews used in electronics to the large structural bolts that hold buildings together. The vast variety available can be a bit overwhelming, but we'll show you a few of the most common types and talk about where they're best used. These are hex head screws, which most people informally call bolts. Because they're cheap, strong, and easy to work with, they're probably the most common fasteners you'll encounter. The only trade-off is that because these require a wrench or socket to tighten, the designer has to leave a fair amount of room around the fastener to accommodate the tool. If you're designing with these, you can reference Machinery's Handbook for a helpful table on tool clearance requirements.
In situations where space is at a premium, you might consider a socket head screw. Since they're driven from the top, you can place them in tight spots or bury them in a counterbore. Low-head screws and button heads have a lower profile and are often used in electronics. A flathead screw can be recessed inside a countersink and is great when you need the head of the fastener to sit below the surface of thinner materials. Screws are most commonly sold with a hex drive, either external in the case of a hex head cap screw, or internal in the case of socket head cap screws, and this is perfectly fine for larger fasteners. But for smaller fasteners, below maybe a number 6, hex drives strip out very easily, and you should consider a more robust drive like Torx. High-strength nuts and screws are sometimes manufactured with an external 12-point drive, which offers more points of contact than the traditional 6-point hex.
It's best to avoid Phillips and slotted drives if you can. While being widely available, they are subject to cam out and can strip easily. Even the construction industry is moving to Torx drive because of the many advantages. There's also a lot of really oddball drive types that were designed for very specific applications or to purposely be obscure. Unless your design fits into these categories, you should probably consider something more mainstream.
You may be wondering what the difference is between a screw and a bolt. Technically, the difference depends on how the fastener is used, not the actual fastener itself. Bolts are used with through holes and are fastened with a nut. Screws are used in tapped holes. Screws have a design for assembly advantage since the technician only needs to use a single tool to fasten the joint.
Screws are most commonly made from either low carbon or alloy steel, but you will also find them made from stainless steel, titanium, Inconel, brass, and aluminum, or even plastics like nylon or PEEK. The primary considerations for selecting material is strength and corrosion resistance. The strongest fasteners are usually made from heat-treated alloy steel, but steel will corrode when exposed to moisture. Coatings are commonly applied to alloy steel fasteners to make them more resistant to corrosion. Zinc plating is economical and is the most common coating on low and medium strength fasteners. It is sufficient for dry environments that receive only occasional contact with moisture. Grade 8 screws usually receive a yellowish chromate conversion coating, which has slightly better corrosion resistance than electroplated zinc.
Fasteners that will be exposed to the elements are often galvanized. This means that the raw bolt is dipped in a pot of molten zinc, which adheres to the base metal. This process is sometimes nicknamed hot dipped, and the resulting coating is much thicker than the electroplated zinc. Galvanized fasteners are typically acceptable for exterior installations.
Aerospace fasteners are usually plated with cadmium. This is a very effective coating, but cadmium is an extraordinarily dangerous material, and these hazards are compelling manufacturers to find safer alternatives. Some fasteners, particularly socket-head cap screws, are coated with black oxide, and while it looks nice, this doesn't significantly improve the corrosion resistance over bare steel.
Coatings are generally not sufficient for applications in which the fastener will be immersed for extended periods. Switching to a stainless steel fastener made from an alloy like 304 or 316 improves the corrosion resistance, but 300 series stainless is not nearly as strong as alloy steel. If you need both high strength and corrosion resistance, you may need to use a super alloy like A286 or 174 pH. Nickel-based alloys like Inconel and Hastelloy are also used in the most demanding applications. Material and coating specifications are defined by standards, such as ASTM, NAS, AS, and SAE, or the former MIL and AN specs. Metric fasteners are defined by ISO or DIN specifications. Various grades of fasteners are sometimes defined by the standards, and for hex head screws, the grade is usually designated by marks on the heads. Metric fasteners use a system of numbers stamped into the head. In either case, the higher the grade, the higher the tensile strength of the fastener. Alloy steel socket-head cap screws generally have a strength similar to grade 8 bolts.
It is important to ensure that the fasteners you are purchasing conform to the required specifications for your product or industry. For example, you may have seen screws like this at the hardware store, where they are typically labeled as panhead screws. Dimensionally, they are very similar to buttonhead screws, and both are made from steel and zinc plated. However, the hardware store screws are made from soft carbon steel, while the buttonheads are made from heat-treated alloy steel per an ASTM specification and are over 3 times as strong. For some projects, hardware store fasteners are fine, but for critical applications, purchase fasteners from a company like McMaster-Carr that lists exactly what specifications they conform to. Fastener materials and coatings is a hugely important area, especially in industries like aerospace, marine, and energy. A particular point of concern is hydrogen embrittlement. During the plating process, hydrogen is often produced, which can become trapped inside the metal's crystal structure. This causes the steel to become brittle and susceptible to spontaneous failure. There was a rash of aviation accidents that occurred when MS jet nuts that had hydrogen embrittlement failed in service. In the corrosive environments common in the marine and energy industries, stress corrosion cracking can cause similar spontaneous failures.
Another consideration is galvanic corrosion. When materials that are far apart on the galvanic series are in contact, and in the presence of an electrolyte, a galvanic cell is formed. In this case, accelerated corrosion occurs on the more anodic material. If the anodic material happens to be small or thin, this corrosion can be extremely severe. Fasteners are available in both coarse and fine threads. Coarse thread fasteners, conforming to the UNC thread specification, have fewer threads per inch and are generally the first choice. However, fine thread fasteners are used in high-performance applications like aerospace and automotive because they have several advantages. Size for size, fine thread bolts are about 10% stronger than coarse thread bolts, and the lower helix angle makes them more resistant to vibration. However, they are easier to cross-thread and don't tolerate debris or thread damage very well.
A slight variation to the UNF and UNC standards is the J-type thread. Instead of the root of the external thread being a sharp V, the J thread has a prescribed root radius. The radius helps improve fatigue performance for cyclically loaded screws. You typically only see this type of thread in aerospace. When designing tapped holes, you need to have enough thread engagement to allow the bolt to be fully tightened to its tensile limit. For threads in most metals, a thread engagement length of around 2 times the nominal size of the screw is sufficient. An interesting nuance of threaded holes is that they don't share the tensile load evenly along their length. In this FEA, we're simulating tightening a steel screw into an aluminum tapped hole, and you can see that the first few threads do almost all the work. Once you get beyond about the 8th thread, there is almost no load being carried. Hence, there is little benefit to additional thread engagement, and it simply adds to the assembly time.
If the tap threads in a workpiece ever become damaged, you can use a component called a helical insert, often sold under the trade name helicoil, to repair them. You drill out the original thread with a drill that's slightly larger than the major diameter, and use a special tap to cut new threads. Then, you install the insert with a threaded mandrel and break off the tang at the bottom. Sometimes people will install helicoils in brand new parts, especially those made of soft materials like aluminum or magnesium. This won't necessarily make the thread any stronger, but it will make it a lot more durable if you will be removing and replacing the fastener frequently.
If you need to thread machine screws into plastic, especially 3D printed parts, heat set inserts create a strong, durable thread. There's typically a special tip that you install on a standard soldering iron, which slips inside the insert and allows you to press it into the plastic. You should do your absolute best to avoid subjecting screw threads to significant shear loads. The decreased area at the root of the thread makes this the weak part of the fastener, and the threads bearing on the mating pieces will lead to fretting. Instead, it's best to transmit shear loads with dowel pins or shear bosses. But if you look at any building built from steel, you'll find thousands of fasteners in shear. Why is it okay there? Structural bolts have an unthreaded section of a controlled length that acts as a dowel. The shearing plane intersects with this dowel section instead of the screw threads, creating a very simple but sound connection.
In cases where you need a fastener to also precisely align components, you might consider a shoulder screw. They have a precision ground shank under the head that can be used as a pin, shaft, or linear guide, and they're a common component in punch and die assemblies. Shoulder screws usually have a much smaller threaded section than other screws, so you can't use them to generate a lot of clamping force. Also note that they're not nearly as strong in shear as a dowel pin, so you shouldn't subject them to heavy loads. Washers are used to help spread the bearing stress of bolts and nuts over a wider area. This is important if you have a loose clearance hole where only a small portion of the bolt head would be in contact with the joint members. Washers also reduce marring of the parts and make torque values more reliable. It's generally best practice to use a washer under the head of a hex head screw as well as the nut. Washers are not often used on socket head cap screws, but to get away with this, it's important to specify a close fit on the clearance hole. An alternative to a free washer is a flanged screw or nut. These are preferred on mass-produced products to eliminate the handling time of a separate washer.
In practice, vibration is the biggest problem for bolted connections in machines and vehicles, and without careful consideration, the machine will literally shake itself to pieces. Applying the proper preload goes a huge way in improving the resistance to vibration. The general guideline is to apply between 70 and 90% of the bolt's proof load as a preload for static joints. Preload is usually controlled by the applied torque. The only trouble with this method is that most of the applied torque is lost due to friction in the threads and between the head of the screw and the workpiece. The materials, coatings, and lubricants all play a role, and a correction factor, called the K factor, is used in the torque formula to account for this. However, even when the K factor is chosen correctly, the torque method is only accurate to within plus or minus 25%.
For statically loaded joints, there's no reason not to apply the maximum preload to the fastener. However, if a joint is loaded cyclically, the fastener may be subject to fatigue, and the preload and fastener material may need to be adjusted to account for the cyclic stress. Another closely related parameter is the grip length of the screw. This is the distance between the head of the bolt and the start of the thread engagement, and the longer this distance is, the more resistant the screw will be to loosening.
Sometimes preload is not enough to prevent a fastener from loosening, and additional provisions must be made. For bolted connections, lock nuts are extremely effective. The most basic style has a nylon element that is deformed by the screw threads and holds the two together. These are called nylocks. In applications subject to higher temperatures above about 250 degrees F, the nylon element will soften and not be effective. Instead, deformed thread lock nuts are used. These come in a few different styles, but in all cases, the threads are specifically made slightly out of round so that they tightly grip the screw threads. You may have seen these bent lock washers at the hardware store. They don't do anything and really have no place in engineering applications. There are, however, other washer designs that are quite effective. These are called Nordlock washers, and they come as a two-piece assembly that is glued together. An interlocking wedge feature causes the two washers to separate as the screw is loosened, which actually increases the tensile load in the fastener.
Liquid thread lockers like Loctite are another good option. There are scores of formulations on the market that are designed for different holding strengths, operating temperatures, materials, and thread sizes. It's important to select the correct formula for your application and fully read the manufacturer's datasheet. Some compounds require special primers and curing procedures or only work properly for certain sized fasteners. Loctite works extremely well on clean parts and screws, but it's somewhat sensitive to residual grease and cutting oil. It's also difficult to visually confirm after assembly that it has been applied correctly or even at all. Mass-produced products often use fasteners with a nylon patch that is pre-applied to the threads. This isn't as effective as Loctite, but it is a lot faster to assemble. There are also proprietary tabs that cut a special thread form that is compatible with standard fasteners. The modified thread geometry creates a locking effect that makes the fastener more difficult to remove.
When all else fails, the most effective way to prevent loosening is to physically prevent the fastener from turning after it's tightened. Aircraft mechanics use safety wire for this, and it's extremely effective as long as it's installed properly. One thing to watch out for is that a fastener that has been properly torqued looks the same as one that's only finger tight. A good practice is to mark the fasteners one by one as they are torqued. Then, a visual inspection will reveal which ones were missed. This special marking wax makes it clear when a fastener has been loosened, either by a person or by vibration. We really appreciate you taking the time to watch our video.
So welcome back. In the video we just watched, there was a significant amount of discussion given to the thread or the thread form of a fastener. And that is one of the most common elements that we discuss when talking about a threaded fastener is the thread. So in general terms, the thread is a helix that causes the screw to advance into the workpiece or the nut when rotated. Threads may be external, as shown here, or internal. So a nut or a threaded hole would have internal threads. So you should be able to identify the pitch, the major diameter, the minor diameter, the pitch diameter, and something else called the lead. And this next video that we'll watch does a really good job visually showing and explaining these terms. The last thing I want to point out is the difference between right-handed threads and left-handed threads. So right-handed threads are much more common than left-hand threads. For a right-hand thread, if a bolt is turned clockwise, it's going to advance towards the nut. So we're going to watch another video that focuses more in depth on the threads of threaded fasteners. I only found this YouTube video series today and I really like it. The creator is an instructor of machine technology at Laney College, a community college in Oakland. I just want to give a shout out to community college teachers. There's some really talented and passionate teachers in community colleges, including this guy.
Hi. I'm Adam. This is the Machine Tech video blog, and today I'd like to talk to you a little bit about screw threads. Screw threads are definitely one of the more familiar mechanical devices in the modern world. We use them to open plastic bottles or to assemble discount Swedish furniture, and they're used in practically every machine in some way or another. It's easy to take them for granted now, but screw threads were truly one of the great leaps forward in human engineering. And the push to create common standards for the different shapes and sizes of screw threads, as well as to invent the increasingly precise machine tools required to manufacture them, were major driving forces in the development of modern industry. So as a technician, or a mechanic, or a machinist, you'll definitely need to know a little bit about them. Essentially, a screw thread is a long wedge with a profile of some two-dimensional geometric shape, like a triangle, that's been wrapped tightly around a cylinder, or in the case of tapered threads, a cone, with each wrap of the wedge snug against the previous wrap. This path, which the wedge follows, is called a helix, and it can be found in many other common objects, like coil springs, or, around this time of year, candy canes. Now, a classic tapered wedge uses the mechanical advantage of an inclined plane to convert force at its blunt end into force perpendicular to its inclined surface, which makes it much, much easier to split objects or to lift heavy objects. Screw threads work in essentially the same way, except that they convert rotational force into linear force along the axis of the cylinder. And this has all types of uses. They can be used for power transmission, precision measurement, making liquid-tight seals. But the most common use of screw threads is as fasteners, used to assemble components by driving an external thread into an internal thread and then wedging something between them. And there are a bewildering number of different threaded fasteners on the market for different applications. Socket head cap screws, button head screws, flat head screws, set screws, hex head bolts, swing bolts. By the way, the difference between screws and bolts is that screws are assembled directly into threaded holes, while bolts slip through clearance holes and are secured with threaded nuts on the other side. And there are plenty of different nuts to fit them: hex nuts, lock nuts, flange nuts, and T-nuts, to name a few. The type of thread that we're going to focus on in this video is the most common type of thread used in fasteners and other threaded parts: the standard B thread, which has the profile of an equilateral triangle with 60 degrees between the sides of the thread. This is by no means the only type of thread, but those other threads will have to wait for their own video. If you look at an engineering drawing or a print of a simple threaded part, like a bolt, here's an example of what you're likely to see. All of the information required to manufacture the threads is specified in a note attached to the threaded portion of the part. The note usually contains at least 4 pieces of information, which always appear in the same order. The first is the major diameter of the thread. The major diameter is the largest diameter of a thread. It's measured over the tops of the crests of the thread. Now, although they're not mentioned in the thread specifications, threads do have other important dimensions. The smallest diameter of the thread is called the minor diameter, measured over the roots of the thread. And the pitch diameter is that diameter where the width of the threads and the width of the grooves between them are the same size. It can be tricky to measure the pitch diameter, but this dimension needs to be closely controlled if mating external and internal threads are going to fit correctly. The second piece of information is the number of threads per inch. This is dependent on how closely the threads are spaced as they're wrapped around the cylinder. You can measure the number of threads per inch simply by laying a ruler over the tops of the threads and counting how many crests there are in 1 inch. Our bolt has 20 threads per inch. This other bolt has the same major diameter, but there are fewer wraps of the thread in a 1-inch segment. In this case, there are only 13 threads per inch. If you divide 1 inch by the number of threads per inch, then you can figure out the distance between any 2 adjacent threads. This is called the thread's pitch. Another way of thinking about it is the distance along the length of the cylinder that it takes for the thread to make 1 full revolution. This is extremely useful information, not only because it ensures that mating threads will actually assemble with one another, but because you can control the linear distance that a threaded part moves just by rotating it a specific number of times. For example, our bolt has 20 threads per inch. So if I turn it 20 full revolutions, then it will advance 1 inch into the part. If I turn it 10 revolutions, which is half of 20, it will advance half an inch. And if I turn it just 1 revolution, it will advance 1/20th or 50,000ths of an inch. Without going into it, this is the same principle used by a micrometer for precision measurement. The third piece of information is the thread series. In our case, we have UNF threads. The UN stands for unified, which is the designation for standard V threads with inch sizes used in the United States. The F stands for fine. Unified threads have standardized numbers of threads per inch for different major diameters. Fine threads have more threads per inch than coarse threads, which are specified with a C. For a half-inch major diameter, like our bolt, the fine series has 20 threads per inch, while the coarse series has 13. As another example, for threads with a 3/4 inch major diameter, it's 16 threads per inch for fine threads and 10 threads per inch for coarse threads. Unified fine and coarse are the most common thread series, but there are a few others as well. The fourth piece of information is the thread class. Thread class refers to the fit between mating threads and the tolerances or acceptable deviations in size used to manufacture them. Class 1 threads have the loosest fit, and they're designed for easy assembly and disassembly, even in the dirtiest conditions. Class 2 threads are considered general-purpose threads, commonly used for fasteners like our bolt. And Class 3 threads have the tightest fit, where precision is the top priority. Now, the A designates this thread as an external thread. The nut that fits our bolt would have a B to designate it as an internal thread. The 4 pieces of information we just discussed will be the only things listed on the vast majority of standard thread specifications, but you may occasionally see a couple of other pieces of information. For example, most threads are right-hand threads, meaning that they're made so that turning a part clockwise advances it into its mating thread. Typically, bolts and nuts tighten against one another when you turn them clockwise. You know, righty-tighty, lefty-loosey. But if you see an LH in the thread specification after the thread class, then this means that the threads are wrapped the opposite way, so that turning the part counterclockwise will advance it into its mating thread. These threads are called left-hand or reverse threads. They're usually used to keep rotating parts from coming loose during operation. Good examples are the pedals on a bicycle, which have right-hand threads on one side and left-hand threads on the other, so the pedal on one side doesn't come flying off while you're riding your bike. This is all fine for inch threads, but most of the rest of the world is on the metric system. Standard metric V threads are physically similar to unified threads, but they're specified a little differently. In this example, we have an M10 by 1.5 thread. Not surprisingly, the M designates this as a metric thread, and the 10 is the major diameter of the thread in millimeters. So far, so good. But unlike the specification for unified threads, which indicates the number of threads per inch, the specification for metric threads does not provide the number of threads per centimeter or millimeter. It actually just states the pitch of the threads outright. So the pitch of this thread is 1.5 millimeters. Finally, although there is a system of numbers and letters for designating tolerance and class of fit for metric threads, honestly, it's a little too complicated to give an in-depth explanation here, and in any case, it's kind of unusual to see it on a print. Well, there's your basic introduction to screw threads, their operating principle, their uses, their characteristics, and how they're specified on a print. And that's it for today from the Machine Tech video blog. I hope you learned something.
Welcome back again. I thought that was another great video. So I'm going to talk a little bit about multiple threaded screws. So one of the interesting differences between threaded fasteners is whether they are single threaded, as shown on the left, or multiple threaded, as shown here. So multiple threaded screws have 2 or more threads cut beside each other. You can kind of imagine it like strings wound around a pencil side by side. So we're going to watch one last video. It's a shorter video that talks about some of the reasons you would use a multiple threaded product. And then for your Knowledge Quest quiz, one of the things you're going to do is upload a picture of a household item that uses multiple threads.
Hello everyone and welcome to SimQuest TV, What's New in SOLIDWORKS 2017. Today I'm going to show you enhanced functionality when using the thread feature in SOLIDWORKS, namely multi-start threads. There are various reasons why someone might use threads with multiple starts. The main one is that it allows the lead distance of a thread to be increased without changing its pitch. This proves useful when fine threads are required, but at the same time you want a quick advance, for example like that on a camera lens. Notice in this example, I have a single thread with a pitch of 1/8 inch. One full turn gives me a lead of 1/8 inch. In this other example, I have a 4-start thread. One full turn here gives me a lead of a 1/2 inch, allowing for a quick connect and disconnect. In both examples, the 1/8 inch pitch is maintained. Another design advantage of a multi-start thread is that more contact surface is engaged in a single thread rotation. In addition, because the lead angle is steeper, less force is required to fully tighten one part onto another, like a cap or lid on a container. Therefore, consumer products that require a tight seal often have threads with multiple starts.
So it shouldn't be too hard for you to find something around the house that has multiple threads. So now for a little bit of random information about threaded fasteners. This is just a picture from the text of a standard hex head bolt. I want to point out points of stress concentrations. So there would be at the fillet, under the head, the start of the threads, and at the thread root fillet. So stress concentrations still come into play with fasteners. Section 8.3 gives some good guidance on threaded fasteners in real life. So some questions to answer on the quiz, for which you'll have to read this section 8.3. What is the ideal bolt length? Why are washers used? Is it good practice to reuse nuts? Why or why not? And in your own words, describe the concept of pretension or bolt preload, which is actually a really, really important component of fasteners and joints. So a little bit of history. Thread forms originally differed in each major manufacturing country, but after World War II were standardized in Great Britain, Canada, and the US to what is now called the Unified National Standard, UNS series. You can also just think of this as English units. A European standard is also defined by the International Organization for Standardization, ISO, and has essentially the same thread cross-sectional shape, but uses metric dimension, so not interchangeable with UNS threads. So if you go into Mustang 60, you would surely find both UNS and ISO fasteners. Both of them are in general use in the US. Both use a 60-degree thread angle and define thread size by the nominal outside or major diameter of an external thread, and all threads are made according to the right-hand rule unless otherwise noted. So I just thought it's interesting, where in the world do people use metric and imperial or English units? So we are definitely in the minority, but we are still a mixed units country. So you'll need table 8.1 and 8.2 on the next slide in your tool. We're going to use both these tables to specify and design threaded parts. So this table 8.1 shows metric dimensions. So you have the nominal diameter, the pitch, and then pay attention up here. Here's the coarse pitch series and the fine pitch series. So they're a little bit different. In the metric system, the thread size is given as the pitch, as that second video explained. In the unified system, the thread size is given as N, the number of threads per inch, also sometimes seen as TPI. So in your quiz, you'll be asked how are metric threads specified. How would you designate a thread with a nominal diameter of 30 millimeters and a pitch of 3.5 millimeters? And then here's our last slide. So this table shows unified dimensions. How does the size designation change as the diameter increases? So notice here on this left-hand column, size designation 0, 1, 2, 3, 4, etc., and then changes to fraction terms. How would you designate a fine series, so UNF, F for fine, thread with a nominal diameter of 0.3125 inches? So again, there's coarse series, UNC, and then fine series, UNF. So that's it for this knowledge quest. Hope you enjoyed, and thanks for watching.